Oh, welcome back, nerds. Today we're going to finish section 2.4. On Friday, we finished up at the very end by figuring out our end behavior based on the fact that this thing had an odd degree, so endings point in different directions, and the front number being positive, telling us we had a positive average rate of change, and the fact that we could easily see what our three zeros were, and all of them had powers of 1 on them, and that's why our graph crossed right through them almost as a straight line at all three of them. The only other thing we really could have done to analyze this graph maybe a little bit better was we could have figured out where it crosses the y-axis. That's really the only other thing we could have done. When you're on the y-axis, what is guaranteed to always be true for any equation? Yeah, x is 0. So technically, I could have easily found this coordinate right here and just thrown in x equals 0 here, and you would have gotten 0, 0, 0, negative 2. So that's the only other thing we really could have included. I don't know if we necessarily need to know that, but I figured I'd throw it in there. Yes, Mark? Yeah.
Couldn't we just find the graph using the second part of that? Why do we need to know the actual equation?
Well, you didn't have to actually know this equation, because if you look this one and the third one, we don't have the actual equation. But I started you off this way because I wanted you to be able to use the leading coefficient to talk about end behavior. And also, it's easier to just see that the the y-intercept is negative 2. Because what's in standard form, you just see it. But if it's not in standard form, you do have to actually replace your x's with zeros. But no, we could have done it. Alrighty. Here, we don't have it in standard form. And we don't need it in standard form. That's not a big deal. We can still talk about what the degree of the polynomial is by imagining that we were doing all the distributions. If you did all the distributions, you'd have this 2x times this x squared at the very front. So what would the degree of this polynomial be? It'd be a degree 4. So we have a 4th degree polynomial. And again, we don't need to do the distribution, but you could imagine this 2x times this x squared, the front number, would it be positive or negative? Positive. So yeah, we'd have a positive leading coefficient. So because we have an even degree polynomial, we know that our endings are going to point the same direction, either both up or both down. And because it's positive on the front, positive people smile, both up. So the endings of our graph look like this, something like this, up and to the left, up and to the right. It wasn't necessary, but I want to go ahead and use limit notation to describe these end behaviors, just so you get used to using limit notation. What? Okay. This one, as we head to the left, we're going to be reaching towards negative infinity on our x-axis. So we say the limit as x approaches negative infinity of our y values is, well, we've already said that it points up. And as we go up on the y-axis, we're approaching the number positive. Well, the idea of positive infinity is not actually a number, but the idea of positive infinity. This one has us going to the right. So as our x's head to the right, they're heading out towards positive infinity. Our y values are going up on this side as well. So they're going to be reaching up towards positive infinity as well. We can see our 3 linear factors here, are 3 factors that have rational solutions. There we go. Those are the words I needed to say. But there are going to be 4 solutions. So this graph is going to encounter the x-axis 4 times. One of them occurs here at what makes this equal 0. Negative 1/2 would make this set of parentheses equal 0. Positive 4 would make this set of parentheses equal 0. But this one isn't factored. And the reason why is because when we do our linear factorization, we typically like our solutions to be rational. And this will not be rational. This will not factor appropriately. Yes?
Why do we know we have 4 solutions again?
Because this has a 0, this has a 0, and x squared minus 2 can be solved for x and get you 2 solutions, which we're going to do right now. We say x squared minus 2 equals 0 add 2 to both sides. And then we cancel our square with a square root. Do you guys remember what happens when you cancel a square with a square root? Yep. We're going to create a plus or minus when that occurs. So we're actually going to get 2 answers there. We'll get x equals positive and negative square root of 2. You would grab a calculator so you could estimate that number, but it's about 1.41. So we have about positive and negative 1.41-ish. I don't know what it is to 3 decimals. I know what it is to 2 decimals. So we have our 4 solutions. We have our in behavior. That's good enough to graph. If you wanted one more piece of information, you could replace all of your x's with zeros to figure out what your y-intercept is. It would be 1 times negative 4 times negative 2. 8. If you wanted to know. So my positive x-axis needs to go out to positive 4. So negative 1, negative 2, positive 1, 2, 3, 4. Graph in blue this time. Encountering the x-axis at negative 1/2, positive 4, and then positive and negative 1.4-ish. I have our 4. And you know what? First degree, and even though this is a power of 2, this could, quote unquote, linearly factor to x plus the square root of 2 times x minus the square root of 2. So again, all of them are crossing through the x-axis. Throw our endings on there. And then cross through the x-axis at every dot. And like I said, if you wanted to know, that was happening at y equals 8. And that is roughly what that graph would look like. I don't know how high up and down the bumps go. I don't know. Doesn't matter. This is just the idea. Everybody comfortable with that stuff? It's not too bad, right? Cool. Let's do it again. Whee! Let's flip it over. Alrighty. Well, hey, look, our factors have powers on them other than 1. That means we're going to get to see some different behavior at our x-intercepts. That's nice. It's not always the same boring thing. If you were to do all the distributions, what would our degree be? Here would get me a square. Here would get me a cube. There it is, a 5. So we would have a 5th degree polynomial on our hands. Bless you. And I just need to know if that leading coefficient would be a positive number or a negative number. It's positive, and here's why. 2x squared is going to give me 4x squared times x a third. I'm going to have 4x to the 5th at the front of my equation. I don't need to know that it's a 4. I just need to know that it was going to be positive. All right, odd degree polynomial. Do my endings point in the same direction or opposite directions? Opposite, yeah. And because the leading coefficient is positive, the endings are going to have a positive average rate of change. So, like that. I'm not going to bother with the limit notation this time. I only did it to review with the last question. Let's figure out where our graph encounters the x-axis. Well, it's just what makes the insides equal 0. So, at x equals positive 1/2, because that'll make 2x minus 1 equal 0. And negative 1, because that'll make x plus 1 equal 0. But what's its behavior look like? At x equals 1/2, because this set of parentheses has a power of 2, what is our graph going to do at that x value? We're going to bounce. Yeah, so we're going to bounce off the x-axis at x equals 1/2. And at -1, are we going to bounce or cross? Cross, but because it has a power of 3, what's it going to cross like? Cubic, yep. So this is cross like a cubic. And if you wanted to know, if you cared, if you put in x equals 0, you get -1 squared, which is 1, times 1 to the third. So 1. This thing crosses the y-axis at 1. There. We know our endings look like this, but I also know that at this value, I'm going to have to cross like a cubic. So I'm going to over-exaggerate that for the notes so it has an obvious cubic look to it. So it's going to come up as we go through. Nice inflection point happening there at x equals -1. And at this endpoint, I know I'm going up, but it's going to bounce there, so it's going to look parabolic right there. So I'm going to over-exaggerate that shape. So cross through like a cubic, but I am going to have to come back down and hit this dot. So it looks something like this. And we know that's a 1, like I said, because you can just plug in x equals 0. So we know there's an inflection point here. We know there's a minimum here. There's an inflection point somewhere here. We don't know where. And there's an inflection point somewhere here. We don't know where. And we don't have a way of estimating that because I don't know where this maximum is. But that's its overall look and shape. How do you feel about that? You guys okay graphing polynomials when they're factored? Pretty easy. That's what I like to hear. Awesome. So let's go ahead and shift gears 100% completely different from the rest of the stuff that's in this material and talk about binomial expansion. I guess the reason why our authors thought it belongs here is because what if you wanted to know what this was in standard form? I don't either. But what if you had to do it? Here is what you would have to do. No, excuse me. Here's what you would want to do. What you don't want to do is go through all of the expansions. Oh my gosh, it's awful. Because there are patterns in our expansions. Anything of the form a plus b, where a and b are just terms, raised to some power, is called a binomial expansion. An expansion would be what you got if you did out all the distributions. Okay. This is kind of a train wreck to look at. It really is. So why even include it? I'm including it because I wanted you to see the patterns that are occurring with the exponents on the terms. Notice the first, I don't want to call it variable, the first term a is always going to start with this exponent here. We say it's n. So whatever this n is will be on the a at the beginning, but it will be on the b at the end. And what happens is every time we scoot over by a term, we lose an a, but we pick up a b. So here it's 3 a's, no b's, 2 a's, 1 b, 1 a, 2 b's, no a's, 3 b's. So like I said, every time we move over a term, we lose an a, but we pick up a b. Also, it doesn't matter which term you choose. Pick one anywhere in that shape and add the two exponents. What you're always going to get is that exponent that you had on the binomial. For example, right here, that 3 and that 2, they add to 5. This 1 and that 4, they add to 5. So on and so forth. The numbers that are in front of all of these variable, let's call them expressions, are known as your binomial coefficients. And as it turns out, the binomial coefficients follow a really neat pattern that we can see in Pascal's triangle. Pascal's triangle is, it's useful. It shows up all over the place in mathematics. It has patterns in it that even blow my mind when I see them. It's just crazy how natural this thing is, how often it shows up by accident in mathematics. I know it's strange, but you do need to say that it begins at row 0. And the reason why is because the row number is actually the exponent on the binomial. So this is row 0, row 1, row 2, row 3, so on and so forth. These are just the numbers that are up in that triangle up above that don't have the A and B in them. That doesn't mean that you're always going to have these numbers. It just means that whatever A was here to the third power and B was here to the second power, there's probably numbers in there. You would have multiplied them by 10. It just means that if you had gone through the full expansion, there would have been like terms that add up to 10 A cubed B squareds, so on and so forth. And in case you didn't know, every row of Pascal's triangle is built by using the numbers in the row before it, simply by adding. Every row begins and ends with a 1. So if I needed the 6th row for some reason, I could easily write that. I put a 1 here, I put a 1 here, and then I just add the 2 digits straight down to get a 6 here, a 15, a 20, a 15, and another 6. And then, of course, I could go dot, dot, dot. If I wanted more rows, I could keep building it. Some neat things about Pascal's triangle. 1, it's symmetric. Because of its symmetric property, a lot of countries, when they do their binomial expansions, they'll actually interchange expression A and expression B. It doesn't matter, and that's these. And that doesn't matter because it's a symmetric setup. The second number of every row is the row number. This is row number 1, 2, 3, 4, 5, 6, so on and so forth. There's a ton of other patterns that I'm not even aware of, but one that is really neat to me. It doesn't matter. Pick a row, add up the numbers in any row. Here you've got 1, 2, 4, 8, 16, 32, 64, 128, 5, 6, 128 times 2, what is that? 256, 512, 1024, 2048. All these numbers I'm saying, do you know what they are? What's that? They're not multiples of 2, they're powers of 2. 1, 2, 4, 8, 16, 32, 64, 128. They're powers of 2. And what's really cool about it is, what power of 2? That power of 2. Row 5 adds up to 2 to the 5th. Row 4 adds up to 2 to the 4th. So on and so forth. Row 10 adds up to 2 to the 10th, 1024. Things like that. Just really cool, I think. But I'm a nerd. I know, it's hard to believe. So yes, we could use Pascal's triangle to expand a binomial. And this one actually is kind of a gift because your A term, its coefficient is 1. Your B term is literally the number 1. So a lot of things will turn pretty for us in these expansions. But this one is being raised to the 6th power. That means the binomial coefficients will come from row 6 of Pascal's triangle, which we just built a second ago. Those binomial coefficients will be, let me write them in red, 1, 6, 15, 20, 15, 6, 1. Just to recall, They're right there. What we have is that our A term is just x, and our B term is just 1. I don't think I've ever fit this in one continuous line. So I'm going to write it really small and see if I can't get it to fit. And I'm going to write my binomial coefficients in red, and all of my A's and B expressions with exponents in purple. This is your expansion. 1, your A term to the 6th, your B term to the 0, plus the next binomial coefficient, 6, your X term to the 5th, your B term to the 1st. Just follow the pattern. Losing an X at each term, picking up a 1 at each term. Not like it matters much because 1 to any power is still 1, but still. We're in the middle. Oh boy, I still don't think it's going to fit. I tried. Yours didn't fit? It's tough. This staple's messing me up. Get skinny, math. You can do it. Yeah. The staple and that hole in the paper got all in the way, didn't it? Like I said, A being just an X with no coefficients or powers, and B being just a 1, these were gifts. It made this very, very easy. This front term is just going to be X to the 6th. This is 6X to the 5th. 15X to the 4th. 20X to the 3rd. Forgot where I was for a second. 15x squared. 6x. And a 1. It's so much faster than actually going through the distribution process 6 times. Oh my gosh. Trying to keep track of all your like terms would be terrible. Just awful. We don't want to do that. You still don't like it? Okay. Yes, sir.
Don't you have to add the 1s?
I did. 1 to the 0 is, but it's times 1. Times 1.
Oh, times.
So it's all multiplication. Like I said, that's why it's a gift. Because if that was any other number, oh my gosh. Now these coefficients would have had multiplied by powers of some other number. Yep. So the next example wants us to use the binomial theorem to expand the binomial. So what is the binomial theorem is the question. For space purposes, I just kind of stuck it at the end of the page just to make sure that it would be on the page. But the binomial theorem is this bad boy down here. Dot, dot, dot means, and this continues, so on and so forth. This right here is the general term of the binomial theorem. It says, if you would like to know any term in the expansion, then we use this formula right here. So you see I took it out, it's right there. These sets of parentheses that you're seeing here, you're not going to say n over 0, n over 1, n over 2, because those imply, when you say things like that, it implies you're talking about fractions. These are not fractions. This is one way of seeing what we call the choose function. we would read this as in choose 2, in choose R. It's combinations. So another way that you could see it is like that, which is actually what the TI graphing calculators show you. And in IB, I've also seen it done this way. I don't ever use that. I just know what it says. This is what's on our calculator. This is what I always use. And yes, your calculator can calculate in choose R. You might be wondering what that is. Well, let me give you an example. Over here to my right, I have a table of 4 ladies. Let's just say I wanted to build teams of 2 out of those 4 ladies. And the question might be, how many different teams of 2 can I build with those 4 people? Well, the answer would be there are 4 choose 2 ways. So if you go to Pascal's triangle, you'd go to row 4. This is choose 0, choose 1, choose 2. There would be 6 different ways to build a team of 2 from 4 people. That's if order doesn't matter. Because if order does matter, it's a lot more. So this choose function gives us our binomial coefficients. And the calculator can do it for us. Let me show you where. If you have a calculator that's using the older operating system, which would be one of the battery-powered black and white ones, or even that thing, it's not going to be in the shortcut menu. So what you'll have to do is you'll have to press Math, and then scroll over to Probability. And it's the third one down, in CR. It means in choose R. So you press the Math button, that's underneath alpha. You scroll over to Probability, and it should be the third one down. If you are using a newer one like mine, it exists in one of the shortcut menus, if you would like to memorize those. Alpha window, and you'll see it's the 8th one down. It's not necessary to know, but I figured I'd show you just because it's there. I'm gonna be real, I don't ever use alpha window. Like I don't have that committed to memory. Alpha y equals for my stack fraction is really the only one of these shortcut menus up here that I use. You can either do alpha window, or you can press Math, go over to Prob, and scroll down to 3. But look what happens when you do it. It comes up like that. Like I said, that's what our calculator is going to show you. And just to show you, 4 choose 2 is 6. So if it's a really old operating system, you would have to do the 4, and then Math, Prob, NCR, then the 2, and hit Enter. If you're curious, of course there's a way to actually find the binomial coefficient by hand. I'm not going to ask you to do that because that is not an AP Precalculus standard that you'd be able to do it. But this is it right there. And in case you don't know, exclamation points are not excited math. This doesn't say in. No, this is pronounced factorial. This says in factorial. Any number factorial means, well, correction, any positive integer factorial means take that number and multiply it to all the positive integers that are less than it. So 5 factorial would be 5 times 4 times 3 times 2 times 1. I'm pretty sure it's 120. 7 factorial will be 7 times 6 times 5 times 4 times 3 times 2 times 1. It's a pretty big number. Okay? Factorials grow fast. And if you wanted to calculate the binomial coefficient by hand, you would have to do it like this. I'm not going to make you do that. We have graphing calculators for that work. This says use the binomial theorem to expand it. Okay, fine. That means write it with all these chooses instead of knowing the binomial coefficients. for the 6th row. So this would look like this. In, which is 6, choose 0. It always starts with in, choose 0. It would be like, I've got a class of, I don't know, they're like 29 of you guys or something like that. I can say, how many different ways could I pick none of you? 1. I just did it. See, I picked none of you. See? So when you choose 0, the answer is always going to be 1. Oh, and just in case it ever shows up anywhere, by definition, excited 0 is equal to 1. 0 factorial by definition is 1. Why, Mr. M? I don't know. I'm be real. But I can tell you if it's not, a lot of math breaks. So it's like also why we say 1 isn't prime. Because if you say 1 is prime, you can do pretty nasty stuff like prove that 2 equals 3 and things like that. So sometimes we have to say things like, look, we just know it's true because if it's not, math breaks. I think this is one of them. Okay. Anyway, this works like this. 6 choose 0, x to the 6th, 2 to the 0. And then there's 6 choose 1, x to the 5th, 2 to the 1, so on and so forth. There will always be n plus 1 terms. So I have 2 of the 7. If you guys will forgive me, I'm just going to do it like that. I mean, it gets all the way down to this. It just means continue the pattern until you get all the way down to here. That's what that means. Okay. But what do they actually equal? Well, you could go through the process of typing each one of these onto our calculator. Or we could say, well, we kind of have them up there at the top of the page. But luckily we do know the 6th row of Pascal's triangle. It is at the top of the page. 1, 6, 15, 20, 15, 6, 1. Yeah, and the 6th row isn't really that hard to rebuild if you really needed to. So what is it going to give us? It's going to give us x to the 6th. This number is 6, according to the 6th row of Pascal's triangle, times 2. So I have 12 x to the 5ths. 6 choose 2 is 15, according to Pascal's triangle, times 4. Now, I know I did ... I kind of cheesed it, right? But the next one would be 6 choose 3 times 2 to the 3rd. Well, 6 choose 3 is 60. 2 to the 3rd is 8. 60 times 8. What just happened? Where did 60 come from? Yeah, I don't know why I said times 3. Anyway, 20 times 2 to the 3rd. And 2 to the 3rd is 8. So it'll be 160. And then we have 15. 2 to the 4ths. 15 times 16. That's 240. It's there. Yeah, there's only one variable, thank goodness.
I know, I was looking for
Yeah. And then there's 6 times 2 to the 5th, 6 times 32, 192. And then there's 2 to the 6th. Oh, I went the wrong direction. 2 to the 6th, which is 64. So yeah, it's a little painful, but you would just type them out on your graphing calculator. Okay? It's not a big deal. This one only has 4 terms, thank goodness. A lot less to write. We'll go with orange. This time A is 3x. Thankfully B is 1 again though. So I have 4 choose 0. 3x to the 4th. 1 to the 0. 4 choose 1. 3x to the 3rd. 1 to the 1. You know what? I know I'm not there anymore, but this 160 doesn't feel right. I think it's 128 for some reason, but I don't remember why I think that.
It's okay. We won't double check you.
Yeah, okay.
Actually, it might be.
Oh, no, that's this one. All right, maybe it's right. Who knows? Okay, anyway, the point is you know how to do it. That's really what I care about. You would type it on a calculator. I was trying to do it in my head. No, it's just faster to do it in my head than to grab a calculator. Okay, I wrote way too wide, so we just spill down to the next line. 4 choose. Yeah, it's only 5 terms. I'm just going to write them all out. I didn't. Oh my gosh, I did that second period too. That's supposed to be a multiplication dot, not an addition symbol. You don't know how I'm getting what? You have to ask me. You can't just murmur it. It's this number. Choose 0, 1, 2, 3, 4. I don't understand what you're not understanding. Look, when it was 6, I had to choose the numbers 0 through 6.
No, like how you got like 60, like 160.
The 60?
Yeah.
That came from right here? Because 6 choose 2 is that number right there. It's, look. This is row 6. This is 6 choose 0, 6 choose 1, 6 choose 2, 6 choose 3, 6 choose 4, 6 choose 5, 6 choose 6. So this is 6 choose 2. Because Pascal's triangle is symmetric, but hold on. So 6 choose 2 is 15, and 15 times 4 is 60. Okay. 15 times 4 is 60. Okay. You want to know why 6 choose 1 is the same as 6 choose 6. From a group of 6 people, how many different ways can I pick one person? 6 of them. Okay. And so we said 6 choose 6 is 1. So it's not the same as 6 choose 1. 6 choose 0 is the same as 6 choose 1. Or 6 choose 0 is the same as 6 choose 6. No, not in a group of 0 people. In a group of 6 people, how many different ways could I choose none of them? 1. I just did it. I just chose none of them. Ta-da! And this one is a group of 6 people. How many ways could I pick all 6 of them? 1 way. I just chose all of them. Okay. Well, anyway, we could go through the process of typing them all out. How about we just pick a representative term instead of spending our time writing them all out, and we'll just type that 1 on our calculator. How's that feel?
Sure.
Let's take this one as a representative term. Can we all agree that it will have an x squared on it? At least? Okay. Math, prob, NCR. So I'm going to do 4 choose 2 times 3 squared. And if you care, times 1 squared is 54. And you could find any term in the expansion that way. Like if I wanted to do this one, 4 choose 1 times 3 to the third, I could do that one and get 128. You just need to know how to use the technology. Oh boy.